So in the last class, we were talking about different CNN architectures, and we went through a lot of different architecture, and then we uh, came to the main problem, and that was like how to train the deeper network. So batch normalization was also giving the guarantee that it can help you to train the deeper network. But again, when you go with the batch normalization, maybe up to 10 plus layers, is it like you'll be able to train the model. But if you're 10 plus like maybe 20 layers or like that, but if you're going beyond that, then there's problem. Then you will be having the problem. And that problem has been observed by all like different researchers. And what they observed that if I'm going with uh, more number of layers, then we are getting this type of curve. And where you can see even your training error is also getting increased and your testing error is also getting increased. So this is the case of underfitting. That means your model is not able to train. Your model is not able to train itself in a proper manner. So you are getting the underfitting case. Okay. So, but why it is happening? Because it was not happening when we had few layers, but when we have added more layers. And why we have added? We have added more layers because we wanted to increase the performance. We wanted to increase the accuracy. But when we have increased the number of layers, our performance has been dropped. Okay. Your accuracy has been dropped. But it should not happen because at least your model, uh, if it is not, your performance is not getting improved by adding the layers, then at least it should give that much performance what it was like what we were achieving before adding the layers. But that was not the case. So it was giving the lesser performance, lesser accuracy when we were increasing the number of layers. Okay, so this was the issue. And even if you go with the batch normalization, that will not help you. So then the idea was this residual network. So what was the idea here? The idea was when we are if you're adding the layers, so at least the new network or at least the new model should give performance at least closer to the or at least the performance that you have got from the old model. It can give even more performance compared to the old model, or it can give the same performance compared to the old. So by adding the layers, your performance, your accuracy should be improved, or it should give at least the same accuracy what you were achieving from the without adding the layers, without adding the extra layers. Okay. So based on this concept, residual network came into the picture, and this is the architecture of the residual networks. So let us see. Let first we just see the previous type of architecture, previous type of we can see the block, and then we'll see the new type of block that has been added in the residual network. So this is the old type of the plain block. We generally add block in this way. So if you see we have X and X is going through the convolution layer, and then we have non-linear function after that, and then we're adding even more convolution layer. So maybe let us give this as a one block. Okay, so if you just recall the if you just recall the BGG or maybe some other architectures, we were following some structure, and what we were doing, we were adding 2 3 convolution layer, and then we were saying that the set of those convolution layer as a one block. Okay, so this is, let us assume that this is one block where we have 2 convolution layer, and we have in between we have non-linear function also, that is ReLU. So what it's doing, it's taking the X, applying the convolution, all these 2 convolution, and along with this ReLU, and then it is giving the output. So if I just tell that this part is something h, that is like function, because again you have the function. So this convolution layer, these all these things are like function that you are applying on the input. So let us assume that this part is h, the combination of these all the layers make this h. Then what we are learning, what we are getting in our output, we are getting this h of x. So this h is taking the x and giving you the h of x. This is the simple block when we are designing the neural network architecture. Now let's see what is the change in the case of residual network. Now this is the architecture of the residual network. This is the block of the residual network. So what they have added here, what extra they have added here, that is your one another direct pass route. Okay, so this is the thing, this is the same thing that we have seen in the case of plain block. Just giving x, applying multiple convolution layer, and learning some function. Yes, you are learning some function over the x, over the input x. And what they have done, they have also added one extra direct pass route. This is also called additive shortcut or identity learning. So what is the function? Now let's see like what is the function. So suppose this part is your f now. So in this case it was h. Now let us take this part as f. Okay. So if this part is f, then what we are doing? We are learning f of x from this part. Okay. And then we are also adding x in that function, in the output of that function. So plus x. Now this is the final thing that you are getting. This is the output that you are getting from this block. Okay. Now let's see like what is the advantage here, how it is helping us for training the deeper network. So first, just see one. Let's go one by one. So the first part is in this case, you were learning the output, okay, from these all the layers or these the set of all those functions. Now in this case, what I'm doing, I'm learning this fx, and then I'm adding the x also. So what I'm saying that if your output is dependent on the input, so it means like your output is also output also contains some information from the input. Okay. So then why should we learn that information? Because if that information is directly coming from the input, then I can directly pass it, and then I'll just learn the residue part. Okay, so I'll only learn the residue part. Okay, so whatever is left. So suppose if your y is, you have to learn something y this, and now you know that this y is also containing, it's like combination of your input and the function, then we can directly give this x, okay, to the output, and then what we'll learn? We'll learn only y minus x. So y is the final output, final thing that we wanted to learn. But since it is dependent on the x. So why should I learn that y fully? Instead, what I can do, I can just subtract the x because I can directly pass x to the output, and I only learn y minus x. So same thing is happening here. So our goal is to learn this hx, the final output. But what I'm doing, I'm learning fx from this model, and we are directly passing this x and then adding these two information, and that's giving the final output. So the one advantage, like this process makes this step or this block makes the this training process fast, because you don't need to learn each and everything. Instead, you'll just learn the residue part, that is your fx. Okay, that's the one thing. That's the, we can say, one advantage of this residual block. Let's see the other advantage. Now, how it is helping or how it is reducing the problem that we were facing in the previous cases. Okay. So first we see like what was the major problem in the previous case, or like when we were training the deep architecture. So when you were training the deep architecture, the major problem was the vanishing gradient issue. So when your architecture, you have a lot of layers in the architecture, like a lot of layers are in the architecture. So what will happen while doing the back propagation? If your values are less or if your values are low, then what happens? It will make if your gradient values, if your gradient values are very low, and every time you are applying the chain rule, like doing the multiplication, so every time it will make the value even lesser. So maybe at the end, you'll just left with the zero, or maybe the values gradient values close to zero, and that is the vanishing gradient issue. So if your values if your gradient values are close to zero, that means there is no update. You'll be not able to update the w. That means you'll be not able to train the model. So this was the issue, and that's why you were facing a problem while training the big large network, big size network. Now, how this residual network is solving it? Because residual network, it claims that I'll solve this problem. Now you can train very large network with this idea, and this is the idea that they have given. So let's see it, how it is helping us. Okay, so if you just see here, and if I ask you, like if I just say you that if you're going back from here, so this is the backward pass. And while going back, you have to find the gradient. Suppose I'm following this path. So if I'm following this path, now what will happen? Suppose these all the local functions, if they are having very low gradient, okay, it's very close to zero. Then in totality, what will happen? Whatever gradient you got from here, like from here, that is like your what we say this uh, what type of gradient we say for this? It's like coming from right hand side. Can you tell me like what is the name of this? Upstream gradient. Okay, so we say this as an upstream gradient. So this is coming from because we have a lot of different layers here. It's not only one block. You could be having a lot of different blocks in that residual network. Okay, this is just one block. So suppose you have a lot of blocks here, and your gradients are coming back, just following the chain rule. And once it comes here, now it is having two paths, this path and this path. Okay. Now suppose this it's going through this path. Okay. And in this path, you know that your local gradient, you'll be also having the local gradient because you have the local function. And based on the local gradient, like you'll be finding the local gradient, and then you'll be multiplying your local gradient with the upstream gradient. And that is the total gradient of the output with respect to this input. Okay, or with respect to maybe if you're finding with the W, then with respect to W. Okay, I should not say input with respect to W. Okay, now suppose your local gradient is close to zero, then what will happen? This overall term, this part will be having gradient close to zero. That means there is no update. And if there is no update here, like if your gradient is close to zero, let us see this part. I'm just talking this part. So if the gradient is close to zero here at this stage, then now this would be the upstream gradient for the previous layer. We'll be having a lot of previous layer also, previous block also. And if every block is getting upstream gradient close to zero, then what will happen? All those previous layers will be not having any update. And this, due to this issue, we were not able to train the deeper network. Now, in this case, suppose this path is giving you gradient close to zero, but you have one another path, and that is the direct path. And you know that you have if you have addition here, whatever upstream gradient you are getting, if your addition here, like whatever upstream gradient, suppose you are getting something maybe zero point 0.9 here. Now whatever value you are getting here, this will be given to this part also and this part also. You know that it is getting distributed to those all those branches, all those two branches. Okay. So 0.9 it will also get, this will also get. But here you have local gradient also, and due to that, this is getting close to zero because you are multiplying this upstream with the local gradient. But when you come to here, suppose this part is giving you values close to zero, but you are also getting info gradient from this part, and which is the upstream gradient that is coming directly to this. And since these two things are getting started from the same place, now these two gradients will be added here. Okay. So in totality, you will be having at least some value. So even this part is not doing anything. If this part is just giving you gradient close to zero, but you have one direct path which is having decent amount of gradient value. And due to that, now you can, even if you go back, here also you'll be having decent gradient for the upstream gradient part, and then it will go back smoothly. And due to this, now you can train very large network. So this was the idea. It's very simple idea, but very, very important idea. It's just like if you're going to Patna, so this is your bypass route. This is your bypass route, and this is your city, Patna city route. So if you're having issue in this route, at least you have this route by which you can go very easily, very smoothly. Okay. Okay. So now this was the concept, and I already have told you. I told you like suppose this part is zero. If this part is zero, like this function is giving you zero, like there's no gradient in this part, then in that case also at least you'll be having the things from here. So in totality, you will be having some gradient. Okay, so this is the residual block. But like if you just see the residual network, so they have just added a set of residual block. Okay, along with fully connected as well as some even more convolution layers. So this is the architecture of the ResNet. Okay, and you can see like these all are like a residual block. So they have added a lot of residual block here. Now, in the residual network, they have also used stem, aggressive stem network, a stem part, which you have seen in the case of Inception. So for the efficiency, they have added this thing. And what this is doing, this is just making the image, uh, reducing the size of the image drastically. So like if you see just these are like few layers, and then even if you just see after this, uh, if you see here, even just adding these two three layers, uh, the image size is getting reduced by 4, and then different residual blocks are getting applied. So you can see after this is the stem network, and then we have a residual block is there. Okay. So they have also like this paper also followed the it has also taken some of the things from the previous, like all those previous papers. So like from the Google Net they have taken this idea so that it can give the efficient, uh, like you should be having the efficient model where the complexity will be less. Okay, so this thing is also there in the case of RESTful model. Like Google Net, it has also not considered a lot of fully connected layers. So instead, just use the global average pulley that we have seen in the case of Inception. So in the case of Google Net, so here also we have a global average pulley. So you apply the stem network, apply different residual blocks, and at the end do the do apply global average pooling, and then go for one fully connected layer. That's all, and that will give the classes for the score of every class. Like if you have 1,000 class, the score of all those 1,000 classes. So we have like different variants of the residual networks. So we have residual net 18, which is having 18 layers. So like you can see here in the stem part, in this part, we have one convolution layer. And then in every stage, like it has been divided into multiple stages. So in the first stage, it is having four convolution layer. In the second, again, we have four, third, four, fifth, four, like fourth stage four, and then finally linear classifier. So total like four, this 16 plus one here, 17, and one is linear. Total 18 layers are there. And in every layer, they have used different number of channels like 64, 128, 256, 512. It's also following the approach of VGG. So starting from lesser number of channels and then by the layers, it is the number of channels are getting increased. Okay, so this is the performance image top five error they have got. So 10.92, and total floating point operation is this 1.8 m million multiplication operations. Now, another variant of this ResNet is ResNet 34, which is having 34 layers, and this is giving again, it's giving error 8.58, so it's lower than this ResNet 80, and this is the obvious because you have increased the number of layers, so either it should give the same performance or it should give better performance, and you are getting better performance here. And the floating point operations are also getting increased. So now this is 3.6. Now, if you compare this thing with VGG 16, so VGG 16 was giving this top five error 9.62, but this number of floating point operation was 13.6 million M. So it's high, very high, like larger than this value. And so you can see like it's better than the performance wise, it's better than this error wise, it's better than ResNet 34, but it's not better than uh, yeah, it's better than ResNet 80, but not better than ResNet 34. But floating point operation wise, it is having very large number of floating point operations. Okay, so they have this residual block, they have also followed this structure like we have seen in the case of this VGG, like taking two 3 by 3 in sequential order, because you know that this is equivalent to one 5 by 5. So we should not apply 5 by 5. Instead, we should apply 3 by 3, like two 3 by 3 in a sequential order. So both the things are similar only. But the advantage, we have a lot of advantage in this case. And those advantages we already have discussed. Those advantages we already have discussed in the previous class. So it will give you it takes lesser memory requirement. It takes lesser memory, then number of floating point operations will be lesser. Then yeah, a lot of advantages are there. They have also, like this is the basic residual block, but in the bottleneck, like if you just see a lot of different architectures are there, a lot of different blocks are there, but maybe at the bottleneck, in between or at the end. So they're like what they have done, they have followed in this manner. So this pattern they have followed at the starting or like for most of the layers, but at the end when we have bottleneck means like we are just reaching to the global features, we are close to the global features, like we already have aggregated a lot of information, now we are reaching close to the global feature. So at this point your channel would be number of channels would be very large, because that we already have seen. So like by the layers, by the stage we are increasing the number of channels, so that information would be stored in the channel. Okay, so at the like when you are reaching to the close to the end, then at that point we'll be having a very large number of channels. So if you are directly applying your filter uh, on that feature map, then what will happen? The complexity will be very large. Number of multiplications as well as your like this what we say this number of parameters. So everything will be very large. So that's why what they have done, they have applied this convolution in this manner. So first, they are reducing the channels. So in suppose you have 4C channel, you have 4C channel at that point. So what they have done, they have reduced the channel to C from 4C. Okay, so just reducing the channel by number of channels by 4 using one by one convolution. And one by one convolution is like cheap convolution. You can it's not costly convolution. So just apply one by one convolution and reduce the aggregate the channel information. And now just go to the C. And now you can apply this 3 by 3 convolution over that. So apply the 3 by 3 convolution. And again, because it is like your channel is 4C, but you have just reduced for doing the convolution, for applying the 3 by 3 convolution. So suppose you have done it. Now again, you go to the same number of channels. So again, you apply one by one filter and go from C to 4C. So in this manner, it will be more efficient. So you can say like they have given, so floating point operation will be a 4HS square, 9HS square, 4J square, totally 17 HWC square. So this is lesser when you directly go and apply this 3 by 3 filter on the input, which is having 4C channel. Okay. So a lot of different variants are there, and you can see ResNet 18, then ResNet 34, and then we have ResNet 50 also. Then we have ResNet 101 also, ResNet 152 also. So they have trained model this residual network till 152 layers, and 152 is like a huge number of layers. And you can see their performance also got improved by every variant. So you can see like started from 18, it's giving 10.92, then 8.5, 7.64. So now you can train, you can take any number of layers and you can train it. But again, if you're going with more number of layers, that will be like, it will be computationally heavy. So you need a lot of memory, you need, it takes a lot of time also. So your computation would be more. So that again, you have to also keep these all the things in your mind. So you can go up to any number of layers. But the thing is like that would be costly also. So that will be like expensive. So you need very good, high powerful GPU. You also need very fast this a lot of like process a lot of code in the GPU so that you can process a lot of things parallelly. Okay. So these all the things are required while just designing or taking any variant of uh, any type of architectures. Okay. Now let's see. So this paper came in 2000 around 2016. That year, like in 2016, one this competition, uh, this a lot of different competitions have been organized, and surprisingly, this ResNet-based model got first place in these all the 5 tracks. So for image classification, again, 150 layer ResNet won it's got the first place. In ImageNet detection, the performance of the ResNet was uh, it's like it was giving 16% better than second. Like it's like 16% better than the network which came at the second position. Again, localization also 77%. So in every track, ResNet got the first place. That's why still people use it. Still widely used. Like it's nowadays in at many places people use it. It's not directly. Even you can use ResNet as a bench, as a base network. But even if you go for some other type of architecture like RNN, LSTM, or transformer, or any type of architectures, there also people try to use, or if you see, they already have used this residual block type of architecture. So whatever residual type of blocks, so whatever architecture you have, try to use a residual type of block so that you will be able to train model, you'll be able to train very large model. And nowadays you can see it. We are having very large model, LLM model, all those large models. So they all are like based on some type of residual block concept. So they are having a lot of different things, but in between they have them. Most of the those type of models have used some type of residual block structure. Okay, so let us just compare the complexity. Okay, so after ResNet, uh, a lot of different architectures came, and initially people used to combine all those previous architectures like if you just see Inception v4, they have combined ResNet and Inception, like GoogleNet and ResNet, because you know that ResNet is also is having some type of it's giving some type of advantages. Inception is also giving some type of advantage. Then why not we should combine the advantage of both? Okay, and then people have done it, and then it has again it performance has got improved. And in this way, like that time, people used to do research in that manner, like combining different advantage, different pros things from different papers, and then making the new architecture. Okay, so this was like later a lot of different type of things also came, like attention mechanism, and a lot of different things came. Okay, now just compare it. And here we are just putting the top one accuracy. So this is the actual accuracy. Top five is like we are giving some flexibility to the model. Top one is like whatever it should give the exact class. Okay. So this is like the exact accuracy that we are finding here. And they have compared the different all those architectures. Uh, Not all, but some of those architectures what we have seen. And what was the observation? The observation was if you just see VGG. So VGG is like it is having highest memory because you already have seen this. It needs a lot of memory to save every intermediate output, and also yeah, it has to save the weights. Okay, so highest memory and most operations. It is having a lot of operations, like lot of multiplication operations. Okay, so it's lying somewhere here. So performance wise, it's also it's decent performance that we are getting more than 70% accuracy that we are getting. Then just come to the Google Net. You know that Google Net is very efficient, and it's taking very lesser complexity. It's like it is having very low computation, less number of multiplication compared to others. So the focus of the Google Net was on the efficiency part, and that's why you can see like somewhere Google Net is here somewhere. So it is having very lesser operations. You can see number of multiplications are very less, and performance wise, accuracy wise also it's very close to the other methods. You can see here it's very like it's close to the ResNet, and even here like close to 70% accuracy. Uh, okay, then let's come to the LXNet. So LXNet, like it was the initial architecture, So you can see like in this case, compute, we had like low compute and parameter was like huge. So lot of parameters, lots of parameters. And so if you just see LXNet is lying somewhere here. And for accuracy wise, it's also giving like, it's not very good for accuracy, but it's close to 55% accuracy. Now come to the ResNet. So ResNet, you just see the ResNet design is very, very simple. Efficiency wise, it's also fine. So we can say moderate efficiency, but accuracy wise, it's giving very high accuracy. And later people has used a lot of different variant of the ResNet, or you can say like they have used the main part of the ResNet along with some other previous type of architectures. Like people have combined ResNet with the Inception. They have, or we can say the different type of blocks of of like from the different previous architectures, and they have combined it. So these are like Inception V3, V4. These are also based on ResNet only. Okay, but they are also having some other, like it is also having Google, the block of the Google Net, and they have combined these two things. Okay, so with that, this part is completed. So I'll not cover the all other architectures which came after 2015, because after 2015, again a lot of different architecture came, but most of those architectures, like they were using some type of some type of residual block, or maybe the different things from the previous architectures. Later, attention based architecture also came into the picture, and so I'm not going to cover those all the things. So you guys can uh, just walk through all those papers if you are interested. Okay, but these are the base architectures, and it was required to understand these all the architectures. So if you understand all these architectures, now whatever new architectures you will be going to look, those will be it will be like easy for you to understand. So there will be like, since you know the designing part, how things have been designed. So now the later things will be easy for you to understand. Okay. So it's my suggestion to all of you that if you guys are interested to read some of the new type of architectures, like which came after 2015, you just read all those, like Inception also, Inception V3 also, Inception plus Google this ResNet, then ResNet is also there. Then a lot of attention-based architecture is there. Architectures are there, so you can just refer to that and you can read it. Okay, so now let's go for one more concept, and which is very very important concept, and that's called transfer learning. Now the question is, okay, so should I? Do you have any question? If you have question, then I'll stop here. Otherwise, I'll just complete the transfer learning, and then at the end, I'll allow you guys to speak. Okay. So I'm assuming that whatever I've explained here, this is fine for everyone. And let us complete this transfer learning, and then at the end, I'll allow you guys to speak, ask questions. Okay. Now, why transfer learning? What is the need of this transfer learning? First, is like, what is the transfer learning? So transfer learning is like we are transferring the some learning. Okay. So in the technical manner, it's like we are transferring some information from one model to some other model. So whatever one model has learned, now we are transferring that information to the some other model. But why it is required? Why we are going for transfer learning? Why we are going information? We are transferring the information from one model to another model. But the thing is, this is required even in our real life also. Suppose here I'm here to teach this deep learning subject. You guys can also learn this deep learning from the book, or from the maybe from some other places. or maybe just say from the book. But if you go to learn this deep learning from the book, if you just walk through the every chapter of the book, it will take you a lot of time. So maybe in a year you'll be able to understand maybe some of the things of that deep learning. Now the same thing you can also learn here. So I am transferring the knowledge. So whatever I have learned, sorry, whatever I have learned, I am transferring that knowledge to you guys. And then you are learning this thing fastly. So this can be happen from the scratch also. Just go an open book and learn each and everything. It will take time, maybe 1 year, and then we'll be able to learn it properly. But if you are following this path, then things will be fast. So advantage of transfer learning is your process will be fast. That's the one advantage. Okay. Like let's dive into that technical term. Okay. So let us see this thing with respect to our CNN or deep learning. So if I tell you to train one CNN network, suppose your client is asking you to train one CNN network, then what you will do? You'll take you'll ask data. Hey, you should give data to me, then only I'll be able to train it. Then what your client will do? He will tell you, hey, this much data I'm having. You just take it and train the model. Then your answer would be this much data is not sufficient because I'm my CNN needs a lot of data, millions, trillions of data. So if you provide that much data, then only I'll be able to train this CNN or I'll be able to train this model. Otherwise, my answer would be no. I'll not. I'll be not able to train model. So whenever you want to train the CNN or any deep learning architecture, any large deep learning architecture, you need a lot of data. Now this is the just seeing this is looking like a very good thing, but in reality, the thing is you'll be not having huge amount of data every time. So some of the public data sets you can get where you can find a lot of data like ImageNet, like some other data set also. Maybe you can find few data sets where you'll be having large amount of data. But suppose you are going to solve some problem which is very specific problem, and suppose that has been given by your client. Now he is not having that amount of data. He will give you just 100 images, 200 images, or maybe 1,000 images. And then he will tell you, hey, train the CNN model. I want CNN model. I'll not take any, I'll not accept any machine learning model. I'll not take any SVM, KNN, any machine learning model. I'll only accept the CNN model. I'll only accept the deep learning model. Now the problem is that you know that you will be not able to do it if you're going from scratch because you need millions of data, millions of images. Now you can also you cannot say no also because you are working there. Then what should you do? In that case, your transfer learning will help you. So transfer learning is here what we do. We take the model which has been trained on the large data set. So suppose this is the LXNet. Suppose this is the LXNet. This is the LXNet. And this LXNet has been trained on ImageNet dataset. Okay. And you have all those weights which you got after this training. So you have those all the weights which you got from the LXNet when it has been trained on the ImageNet dataset. And now what we'll do, so this is the data set. This is the architecture. This is the model that you have trained on the ImageNet. And now you have the small data set. So you know that you cannot train every part of this from the scratch. That's not possible because you have very small data set. You have only very small data set. And also your classes could be changed because in this case, they have trained this data set, and in that data set, they were having 1,000 classes. In the ImageNet, we have 1,000 classes. But in your case, since your client has given that problem to you, so number of classes would be different. And this would be even lesser than this. Maybe you have only C classes. So now the thing is, you know that you cannot train this whole architecture from the scratch. Because in that case, what will happen? You may get underfitted model, and that you don't want. You want proper model. So now what you'll do, since you know that already this architecture has been trained on the larger data set, ImageNet data set. So why not we should take these all the things from here, take it from here. So take all the layers, whatever layers we have here, all those layers from here, and at the end you just use one more fully connected layer because in your case your number of classes are different. So you have to go to the C classes. Here they were going to the 1,000 classes at the end, 1,000 values. Now you have to go to C number of values. And then what you'll do, you'll train some of the part of some of the parts of this network. So these all the things, these all the parts, or these all the layers, you are not going to train it. So maybe in a very like maybe if your data set is very small, then you might be training only this part, this part, and then freezing all this part. That means you are not going to touch it. Whatever you had in this case, you just take it as it is, and then you just train this part because this fully connected is totally new and which is going to learn this C classes like C class classification. So just train this part, only this part. Okay, and again we'll see a lot of things later. Which part we should freeze or which part we should train. So all these things will come later. Okay. So this is just one example that I've given you. So if you have very small data set, just maybe train the last layer. That's all, and just keep all those values here. All those the weight values as it is. And people have done this thing in the past, and they observe that when you do this, like find this. Okay, so how can you say that this is like transfer learning? So your learning is getting transferred here. How? Because you already have used these all the values from this model. Okay, and this model is coming from the ImageNet data set. You got this model from the ImageNet data set, and now you're using that model for some other data sets for solving some the similar type of problems but for the different data set. And there you are having the different number of classes. So you're using these all the knowledges from this model. So it's like the transfer of knowledge is happening here. So people have done this thing. This is also called fine. Some way like we'll come to that fine tuning part. So this is here it's not exact fine tuning, but yes, this is sort of fine tuning, and we'll again come to that part. So fine is some sort of fine tuning is happening, and people have done this thing, and then they observe that doing this fine tuning, performance got improved. So like this, you can see here.
from here to here, you reach maybe some improvement in the performance. Okay. Okay. So for a very small data set, maybe you can just train one like the layer that you have added. You just train that layer. But suppose you have slightly bigger data set. Suppose your client is coming and say, hey, I have good amount of images, like 10,000 images for these C classes, or maybe 10,000 images. Then what you can do, then you'll not you'll be not only training the last layer. Instead, you'll pick few more layers. So like this FC4096, these are coming from this only. Okay, so all those weights are just you're just transferring from this to this. In the previous case, we were just training the last layer, and remaining layers were like freezed. So we're not touching those layers. So when I'm saying training, that means you are going to change the W. So that means you are going to find the gradients and then you are changing the value. So now if I'm saying that this is freeze, that means I'm not going to change the value of these all the filters. So in this case, they were just training the last layer. But if you have sufficient amount of data, then maybe you can go for picking few more layers like this. Here, you can pick all those fully connected layers. So just train this part. Okay, so this is also called fine tuning because this model you already have got from here, and then you are just fine tuning it. So these are all the layers you can see 4096, 4096. These are all the things you got from here only, from here only, and now you're just changing it so that it will work very good for the given data set. So you are changing these all three things, or even if you have larger data set, then you can also go for even more number of layers, and you can train it. Okay. So with the bigger data set, you can train more number of layers. Okay. Now, whenever you're doing the fine tuning, so what generally is going to follow uh, your learning rate, whatever learning rate you are going to choose, it should be like 1/10 of the original learning rate. That is the good starting point. Why? Because you already have got the good model because this is the good model. But for for the particular data set, now you are just taking that the good model of the particular data set and then you are going to use it for your data set. So since you are not starting training your model from the scratch, now you are starting you're training your model from the starting points which you have got from this model. Okay. So this model is giving you the weights, and that could be considered at the starting point of this model, which is going to solve the particular problem. Okay. So if you are doing this now, if this is called fine tuning, if you're doing it, it should go slow. And even in this case, you are training this last layer, which is which is which is happening from the scratch because last layer was not there. FC minus C. This was not there in this case. So there, like you should be having like this guy is not knowing nothing at the starting. These are like expert. These guys are like expert. But for this task, they are not expert for this task because this is a different data set. So that's why when you are transferring this knowledge and you are just refining these all the guys for doing this task, it should go slow. Otherwise, it will overshoot. So generally, we take the low learning rate so that it should go in a proper manner. Because these all the guys are expert in this task. They are not expert in the task what you are going to uh, do in this case. So that's why if you're just taking the help from these all the guys, these all the expert, we should go slowly. it should go slow so that it will adjust, they will adjust themselves, and then you will start getting good accuracy. Okay, now if I just say you, if maybe if I ask you, like which type of features, which type of information we learn by the layers, then your answer would be, hey, at the starting, since I'm giving image, and at the starting, my convolution filter is very small. So my context is very small. So maybe just applying 3 by 3 filter at the starting, just on the image, I'll be able to learn very small features like edges, maybe color, all those very small features. So initial layers, if you just see all those initial layers, these all the initial layers are just learning the small level features, edges, colors, and all those like shape, very, very small structure, small shape. Okay. So these all the informations or these all the features are like very generic features because these are like common across all like across most of the data sets. So even if I see color, edges, so these all the things will be there. Even I consider ImageNet data set or maybe I consider some images data set which have been given by my client. So these all the features will be similar only. So edges, color, and like that. Okay. And all these initial layers are learning those generic features, or we can say very common features, which are common across all those across most of the data set. But just by the layers when you go in a forward direction. And maybe once I reach here, fully connected, you know that once you are reaching to the fully connected, before here, you'll be having features very, or you'll be having very, very, what we can say, like uh, very specific features. Because these are all the layers, these are like giving you some type of global information. And that information would be helping you in doing the particular task. So suppose you are doing the classification here on the ImageNet data set. So at the end, it should give the discriminative features or discriminative information from the image so that you'll your model will be able to give the appropriate class. Okay. So at the end, you'll be having very, very specific features. And those features will be very, very specific to the data set for which you're solving the problem. It will be very specific to the your problem statement and the data set. Okay, so this is very, very crucial point. So that's why I have given I, I try to give some attention on this part so that you guys, because this is very, very useful. Okay, very, very useful. These all the information would be helping us defining a lot of different things later. Okay, so these are like very, very specific features, and then we have more generic features here. Now, let us consider the scenario when or what type of strategy we should follow for the transfer learning. So suppose your client has given you very little data. Okay. And what he's saying that, hey, you train it, you solve this problem. You just do the classification. But I am only having this much data set, very little data. But what you observe that whatever data set your client has provided to you, this is very similar to the data set on which you already have trained this model. And that is your ImageNet data set. So if this data set is very close to the ImageNet data set, then how to train the same model or the same architecture for this data set? The answer is very, very simple. What we'll do, just train few layers at the end, just like the previous. So maybe I just train the last layer of this. So what we'll do, just at the just use the linear classifier on the top of on top layer, like we already have seen in the previous slide. So this is the scenario. So I just add one more layer, which will do the, like this is the last layer that you are adding here, and all these layers you will be just freezing it. So you are not going to train it. You're just training this part so that it will be able to do the classification, like C class classification task. Now the second scenario is, suppose you have quite a lot of data, and those all the data, suppose you have client has given you the data, and you have that sufficient amount of data, and this data set is similar to the ImageNet. Now you know that you already have trained the model for this ImageNet. So if you have sufficient amount of data, so what we'll do, we'll just take maybe few more layers, because you know that at the end we have very specific features. It learns, it gives you very specific features. So if you are at the end, so like if you're going for fine tuning it, if you're going to use this model for your data set, then why not we should train few more layers at the end, because you know that is very required thing. You also want very specific features for this data set. So that's why, yes, so that we can learn the more specific type of features for this data set. Okay, so that's why you can go for the few more layers. Now the thing is, if you have very little data and this data is very different than ImageNet, now what will happen? Suppose ImageNet is doing 1,000 class classification on the natural images, and now whatever images have been provided by the client, this is totally different image, like maybe medical images, which is having different type of information. Now how should we proceed? It's just like uh, I'm teaching here deep learning, but you want to be expert in like some other, maybe in robotics, or maybe in maybe in semiconductor devices. So if you learn from me, then what will happen? You will be in trouble. So transfer learning should go in a proper manner. It should not be the case that you're doing the transfer learning for totally different type of problems, or totally different type of data set. Okay. So if you have very little data and very different data set than ImageNet, then you are in trouble. So you can just try linear classifier from different stages. You can try different things from, maybe try different, just add maybe add different classifier. Maybe just on the top of it you can add linear classifier, or maybe on the top of it just do trial and error. And if it works, then it's good. If it does not work, then there is no any alternate option. Now, if you have quite, suppose you have quite a lot of data and it's very different data set than ImageNet, then now you know that you have sufficient amount of data set. So what you can do, even you can fine tune or larger number of layers. Maybe you can fine tune a larger number of layers, because at the end you know that it's very specific features. Then why not we should train all those layers which are giving very specific features, or maybe whatever, like maybe up to here. It depends like how much you can. It depends on your data, how much data you have, or maybe if it is not uh, fitting very good, then what you can do, even you can train from the scratch. Just train it. Don't use any model from the don't use weights from any pre-trained model. Just train your model from the scratch. That option is also there. But again, it depends on the data set, how much data you have in that data set, and what is the challenge, how much challenging data set you are having. But mostly it is depend on the how much data set you are having, how many samples you are having. Okay, so transfer learning is like a very good option. So whenever you have lesser amount of samples, you can think about the transfer learning. And people have used this thing in the past. They have used it at multiple places. Like you can see here, this is object detector, also called fast RCNN or faster RCNN, faster RCNN. So in that they have used like the base block. You can see here. This base block is coming uh, from the uh, from the pre-trained model. So you can just pre-train any model and then you just use that box here. So this box is coming from the pre-trained model. Even in the case of image captioning, you know that like image captioning is like you have given the image and you have to describe the image. So there we use CNN as well as RNN because text is also involved. So for text you have to use RNN, but for the image you have to use CNN. So even in this case, people have used this pre-trained CNN for getting the information or the features of the image, and then after getting this, then it is given to the RNN for getting the sentences or paragraph for describing the image. Okay. So, even if you're going with the transfer learning with CNN, architectures also matter because like they have observed this thing. Just uh, changing the LXNet was when it was they was giving the then LXNet that it was 15 then 19. So by the just changing the architectures, performance was also getting changed. So architectures also matters. So that's so when we were doing this transport learning, you also need to keep this thing in the mind. Like we can see from here to here. Okay, so you can transfer learning is the option that you can choose. Many times you can choose it. Like whenever you have lesser amount of data and you are going to solve it, then you can go with the transfer learning. Even if you have larger amount of data set, in that case also you may prefer to go with the transfer learning when we have very similar type of data set. So suppose ImageNet on which your model has been trained, then you know the model, you have the model of the image, you have the model which has been trained on the ImageNet, and now you're thinking to use this model for some other problem, and for that problem also you have sufficient amount of images. So in that case also you can take the advantage of transfer learning because again you know that you can also train that your model from the scratch because you have that amount of data set. But the thing is if you are going from the scratch it may take a lot of time. So why not we should start from the good weights and then we can proceed. So transfer learning is always good, but again also you have seen the scary like that particular issue. So when you have very different data set, then you have to think more. Okay. And let me just tell you, even transfer learning does not work every time. So if your data set is very low, very less, your amount of samples are very low, very less in that case. Let me suppose you have only 100 images, 500 images. So you might not be able to even might not be able to get good model doing this transfer learning. So in that case, you have to find some alternate solution. So there are a lot of different solutions. So one is like image based training that could also a lot of different things are there.
which can be used when you have very limited amount of data set. But transfer learning is again one way where you can train the model even if you have limited amount of data set. So do apply it in whenever you are deploying, you're making some model. But if you just use it, if it is not working, then you can go for some alternate solution like Siamese network or maybe some different type of approaches. Okay, so with that, we are done with the CNN. Now, in the next class, we'll start RNN. So I'll allow you guys to speak. Any question from from today's class? Otherwise, we'll stop. Okay. So I'm assuming that there is no question. Then thank you.
Yeah. Thank you, sir.
Thank you.